Hello, my name is Haocong Cheng. On behalf of our team, I will be presenting our work, CrowdIDEA blending crowd intelligence and data analytics to empower causal reasoning. Causal reasoning is the process of understanding and explaining the relationships between different events, examining the context and circumstances in which they occurred, and drawing conclusions about what could have led to a particular outcome. Albeit the progress, several challenges remain when people conduct causal reasoning with quantitative data like data analytics. For example, people may have cognitive biases when interpreting these quantitative data, and it is often difficult to determine which variable is causing the other to change. Therefore, prior work suggests that sharing qualitative data like shared causal beliefs could help people conduct causal reasoning. A recent work suggests that sharing other people's causal beliefs could help other people discover more alternative hypotheses during their causal reasoning process. However, these qualitative data may lead to social biases such as groupthink and conformity effects, and they may not always be correct. When blending these two techniques together, little is known about how people conduct causal reasoning when they are exposed to both cross-causal beliefs and data analytics. Nor has the literature evaluated effective designs for delivering aggregated cross-beliefs to inform causal reasoning. In this work, we aim to answer the following research questions. Arq1. What's the effects of integrating cross-beliefs and data analytics on people's causal reasoning outcomes? And Arq2. How do people leverage crowd intelligence and data analytics in their causal reasoning processes? To answer these two research questions, we designed and built a system, CrowdIDEA. There are three main panels. On the left is the crowd panel that presents cross-causal beliefs. There are two design options that will be discussed later. On the right is the data panel that presents data analytics, and in the middle is the diagram panel where users can draw their own causal diagrams. There are many ways to design the representation of the cross beliefs and how people can interact with it. To explore this design space, we experimented with two different designs. The first one is based on Ben Schneiderman's visual information seeking mantra. Overview first, zoom in filter, then details on demand. We call this the overview design. Here is a live demo of the overview design. In this design, the crowd's beliefs are represented by an aggregated causal diagram. The thickness of the arrow is proportional to the number of people in the crowd that have drawn this arrow. When users click on it, they can review the narratives. The data visualization will be auto-plotted at the same time to help their reasoning. Then, they can add the arrow with one click, or they can also draw the arrow manually. Whenever a new arrow is drawn, the crowd and data panel will be updated. On the top left corner, they can also click on the Show Diagram Difference button to compare the crowd diagram and their own diagram. The blue arrows are the ones that do not appear in user's diagram, and the red arrows are the ones that are reversed in user's diagram. The second design was based on principles proposed by Frank Van Ham and Adam Perrier. They suggest to let users search for a focus first, then expose more context, and expand more information on demand. We call this the focus design. The focus design looks like this. Instead of directly showing the overview of the crowd's beliefs, the system only shows the relevant information when the user is focusing on a relationship. For example, when the user draws an arrow, the system will show that how many people in the crowd also drew this arrow, and how many drew the reversed one. In addition, the system provides more ideas from the crowds. The listed arrows down here are the ones that are related to the current focus variable and not appearing in user's own diagram yet. This feature is designed to help users to expand their diagrams. The data panel is the same for both designs. The system will automatically present the data visualization and regression results in real time. Users can expand to see detailed statistics for each variable. Then, on the top right corner, there is a feature called Show Significance, which will color the arrows based on the regression results. If the corresponding coefficient is significant, the arrows will be green. Otherwise, it will be gray. For the user study, we adapted a dataset with 7 variables from a safety reporting app, which enables a member of the university to submit a safety-related report, to which the security agent can reply directly through chat. To collect the crowd's causal beliefs, We conducted a pilot study with 20 participants by providing them only the diagram panel and the 7 variables, and asking them to externalize as many possible hypotheses with reasons as possible. For the user studies, we recruited 54 participants who had prior experience with data analysis using regressions. Participants were randomly assigned to one of the 3 condition groups. 18 participants received the overview design, 18 received the focus design, and 18 received the control design that did not include the crowd panel. During each study, after tutorial and practices, participants were asked to create a complete causal diagram in 20 minutes using the information presented on their interface. After the task, participants were then interviewed to learn more about their experiences with the system. To answer RQ1, we quantitatively compared the system logs and the participants' causal diagrams. We found that participants were inspired by the crowd's beliefs and realized that there were more causal relationships that might exist. By conducting manually used tests, we found that compared to participants with the control design, the overview design led participants to include significantly more causal relationships in their diagrams, remove significantly fewer errors, and use the data panel significantly less often. Based on these results, we would expect the structure of the generated relationships to be significantly changed. However, by comparing the participants' causal diagram to both the data generating model and the crowd's diagram, we did not observe any changes in similarities in graph edit distance among any of the 3 condition groups. This shows that despite having both crowd's beliefs and data analytics, participants did not blindly follow either of the 2 information sources. To answer RQ2, we qualitatively analyzed the post-study interviews to identify the strategies participants used to conduct causal reasoning with our system. For the crowd panel, we identified 2 major strategies. The first one is to bootstrap causal relationships by browsing the crowd diagram and the narratives. Participants use the crowd panel in their early stage to identify causal relationships commonly added by the crowds that could more likely to exist, and prioritize reasoning those relationships. They also read through the narratives to determine the direction of the arrow. The second strategy is to deepen causal reasoning by comparing with the crowd's beliefs. After completing an initial causal diagram, participants further compare with the crowd's causal beliefs. If they found crowds supporting their added arrows, they feel more confident about their diagrams. If they notice the majority of the crowds disagreeing with the relationship, they will review the narratives and decide whether they would like to add an arrow, remove an arrow, or change arrow direction. The crowd panel allows people to interact with subject causal beliefs, and the data panel presents objective views of the data. We found that they provide complementary support for participants to improve their causal reasoning processes. Specifically, we found that participants were able to use crowd's causal beliefs to understand unexpected data patterns. The narratives in particular were used by participants to look for explanations to the data patterns. Meanwhile, participants noticed some credibility issues with the crowd's beliefs, such as wrong or misleading narratives. In these cases, they will refer to the data analytics to make decisions. In fact, most of the participants who noticed conflicts between crowd's beliefs and data analytics follow the data in their decisions to keep or remove an arrow. Participants also adapted strategies to leverage both information sources to avoid being biased by one of them. For example, half of the participants from the 2 treatment groups noticed that their crowds may introduce biased views during the task. Some of them only reviewed the crowd's beliefs after they created an initial version of the diagram based on their own beliefs and data analytics, so as their views were not biased by the crowds at the beginning. Our findings provide a few theoretical implications. For example, we expanded an existing knowledge-generating model with 2 reasoning processes: inspiration and internalization. We observed that participants were able to use crowd's beliefs to inspire them with more alternative hypotheses that they may not think of. This is the process of inspiration. Participants were also able to use the crowd's beliefs to gain insights from the data results, such as get explanations of why 2 variables could be causally related as shown in the data. This is the process of internalization. Our study also shows that incorporating data analytics and crowd intelligence in causal reasoning process reduced the negative effects from one information source. However, an effective interface design is also important. For example, while the overview design poses a significant effect to causal reasoning outcomes, it could be more useful in exploratory data analysis that focuses on discovering new possible hypotheses rather than drawing rigorous conclusions. Thank you for listening. If you have any questions regarding this research work, please let us know.